Up next, underwater inspections, imaging to monitor Scour and Scour Countermeasures by Michael Dukes with Consor Engineers.
Appreciate you having me here. We'll be talking about using acoustic imaging to monitor Scour and Scour countermeasures. Quick blurb on Consor. We inspect nationwide, do transportation, as well as water and wastewater engineering around the country. I'm out of our Oklahoma office, but work coast to coast and even off the coast, sometimes up to Alaska. And if I'm really nice, Jeff will send me to Hawaii once a decade or so. So at the end of this presentation, you'll understand the basics of sonar. We'll talk about the 2D sonar or single beam sonar advantages and disadvantages, as well as 3D or multi-beam sonar advantages and disadvantages to monitor Scour. And then we'll touch on a case study of a single bridge that we've inspected over the last 8 years or so, diving using 2D sonar and 3D sonar, so we can see how that site's been monitored with the various technologies in a very direct side-by-side comparison to see them in action there. So for our basics, sonar is actually an acronym, stands for sound navigation ranging. The speed of sound is rather consistent through water column, dependent on salinity, temperature of the water, and depth. But with that, we can take advantage of it. And it varies a little bit throughout the depth if we get thermoclines, but for the most part, it's very consistent and a known value that we can calculate. So if we have a transducer to emit a sound wave, it goes through the water, bounces off an object, whether it be a pier wall, something on the channel bottom, or anything in between, comes back to where it was emitted from, and the receiver captures that return sound wave. We know what time it left, what time it came back, the speed it was traveling, so we can plot a distance and know how far that sound wave traveled. So using a little math, we'll take care of that, and the computer programs that have been developed over time, now we'll plot those returns as actual images. So that's kind of the most basic understanding of sonar in a nutshell. That's been well crafted over the years to give us single beam and multi-beam sonar that we've taken advantage of in the bridge industry. So our heavy hitter in the bridge industry over time has been our single beam sonar. You'll hear it referred to frequently as 2D sonar. So a little schematic on the left here, you have a computer, a driver box, so that sends all your ones and zeros through to send that sound wave out of your transducer, get it back from your receiver, process it. And what we see in the field on 2D imagery is that circle on the top right. And it's been referred to a lot over the years as real-time video using sonar. It's not truly a video. As you see, the shape of the sound wave in the middle is kind of a fan shape, so it's like 0.9 degrees in width, 30 or so degrees in the opposite direction. So that footprint hits and returns back, and we'll click over basically half a sonar beam width at a time, stack those up, and that's how we get that image on the top right that we can pull measurements from in 2 dimensions. The shape of our transducer is going to directly affect the shape of our sonar beam. So if we've got a circular transducer, we'll basically send a circular sound wave or get us a dot return. So single beam hydrographic survey uses these. Your digital handheld sounders are going to use that, just send a dot of sound, get one return from the footprint. Once we stretch to a rectangular shape, we can get the fan beam that we typically use to get a nice big area that we're looking at, and we'll be scanning, put it on a rotator head. And in the bridge inspection world, we'll take that sonar head, turn it sideways, and that blue beam is basically the shape of the sound wave that we're sending through the water and listening for the return. So distance-wise, we're going to plot very accurately. One challenge that takes a little time and experience to interpret data is within the width of that beam. You don't have, once you plot it on a 2D screen, any idea whether your return was on the right side or the left side of that beam per se. So it's just going to plot and return. So once you start getting in between fender piles and stuff, you really got to interpret shadows to know where in the beam wave that return's coming from. So that can take a little bit of skill to process, but it's very useful in getting us a height of footing exposure, height of seal exposure, and start getting heights and certain limits on scour holes. Over time, we've shifted to also using multi-beam sonar. There's lots of different iterations of this. In its most basic sense, you're going to send a lot of those cone waves out. Some systems send a single line out of 128 or 256 or some multiple of beams, so it'd be a straight line of beams. We're going to send the sound wave out, listen for it, and plot them all, dots in space, creating a point cloud. We have moved to using the Coda Octopus Echoscope. It's a volumetric multi-beam sonar, so instead of sending one line, it's got 128 by 128 grid of beams, so you're sending out 16,000 sound waves at a rate of about 12 times a second to build a very dense point cloud in real time very quickly. So once we start shifting to multi-beam, the 2D's a stationary deployment typically, but multi-beam, we're doing it on the go while the boat's traversing typically. So if the boat's rocking and rolling and we shoot a sound wave here and then it rolls, we got to make sure we don't accidentally plot it over there. So you have an inertial reference unit, which, if you can see, the boat is the kind of little blue box up on the pole. It's got a gyroscope, and it's doing those mathematical calculations to take into account the boat movement and make those corrections so that each point in that point cloud gets the correct XYZ coordinate. I also have two GPS antennas integrated into there to track position. So those are our basics of sonar theory, 2D sonar, 3D sonar, how they operate and collect data. So we'll touch briefly on some of the advantages and disadvantages of each system. So with 2D, very quick setup and teardown. Once you're on site, you can probably get everything plugged in, ready to go in 15 minutes or less. So very mobile. We can hit a bunch of sites in a day or a bunch of piers to get that data. Sonar in general, you'd like to have over 10 feet of water. You can scan and collect data in shallower water. However, you start getting lots of multipath returns where maybe the sound wave hits the bottom, hits the surface, hits the bottom, and comes back. So you get additional returns and a lot of scatter going on. It's not real data. So over 10 feet is desired. We can gather stuff less than that. It just creates a few challenges. Lots of deployment options with our 2D sonar, whether it be a surface swimmer, from a boat, from a hydro platform, from a snooper truck, from the diver. It's very versatile, easy. It's just one cylinder. With a PFD, it's about neutral for the surface swimmer. We'll see some examples. Graham talked yesterday. One thing we can do at this conference is share our warts. There's a few bad images I'll share just to demonstrate some of the challenges that we either have to overcome with 2D sonar or that create a limitation on it. And it's in a single plane typically. So speaking of the deployment options, this large photo on the bottom left is actually an abutment with a pier built on top of it. As you can see, the water depths along the fascia of the bridge are much shallower than along the face and underneath it. And it's a very low clearance between that bottom beam and the water surface. With the multi-beam, we're typically driving a boat underneath, so to 2D, we can go deploy a surface swimmer to collect that data. Top right is a very remote, small waterway with high velocity. We were able to match the boat speed to the waterway speed to scan that just to make sure we had continuity of that pier wall into the channel bottom with no footing exposure. The 2D is really capturing a moment in time in a single plane. So as we stack, we're going to basically get a picture of what's going on in mostly a single plane. We're not getting any horizontal depth to our photos. That can be all we need sometimes. If we have a deep foundation, a drilled shaft per se, we just need to make sure we have continuity into the channel bottom. We know the tip elevation, so we can use it to gather the depth. Here, we had a pile cap footing become undermined during a flood event, and we were able to quickly assess exactly how much pile exposure we have. We're not looking for the condition of the piles with the sonar, just what that exposure was. We'd be able to see if there's a footing or a seal exposed to be able to rapidly collect that. On the left, we have a pier sitting on top of a rock shelf. We can see that a little footing exposure, but it's bearing there, but we don't have the depth perception back into the page to see where the edge of that rock cliff is from the perspective that this photo's at. In high velocity waterways, the velocity of the water itself isn't inherently going to cause you to get bad data. With multi-beam, we can go in very high velocity. But when we need the stationary 2D deployment and we have to get right up against the pier, we can get air bubbles that basically sit on the sonar head. So on the picture on the left, those black dots or black streaks is a couple of returns where we had an air bubble sitting on the sonar head. Speed of sound is drastically different through air than it is through water. So it basically creates some blank spots on our scan. We can also get lots of air bubbles in the water column that can really distort our image, or we can't penetrate through it, so we get almost a lot of washout. And then with scour being most severe at the upstream nose of a pier, once you get into high velocity waterways, 5, 6, 7 foot a second current on the Mississippi and Missouri rivers, it can be very dangerous to try to nose in a boat to the upstream side. You got a 2 to 3 foot hydraulic sitting up there. And if it overturns your boat, you're in for a pretty bad day. So that can create a safety challenge just to access that upstream nose. And then the sea state. We need a stationary deployment because remember, it's just plotting how far that sound wave traveled. So if my boat's moving and the sonar head got closer to the channel bottom, further from the channel bottom, closer to the channel bottom, further from the channel bottom, even if the bottom's flat, like you see on the picture on the left, it'll plot as it's wavy because it's just doing that distance. On the right, it's giving us the data we need to know those columns are continuous, and we don't have footing exposure, but because of that sea state, that column that is straight is getting plotted as having some waviness and curvature to it. So that's understanding the limitation to it, but it's getting you the data you need to know that that's continuous. You don't have footing, but it's just not presenting as pretty because we had that rough sea state. We don't have any depth of penetration horizontally, so on the picture on the left, that bridge or that pier is not floating. It was actually built with pile exposure, but because of the shadows, like my sonar head's up here looking down, I can see this face, but if there's another step out, I can't see around and underneath there. So I can get the height that we have of undermining, still gonna need to go under there to get hands-on for pile conditions, but if we knew that was an as-built condition, maybe we're not as concerned with the volumes of that scour hole, so 2D might be fine. If this is exposed due to scour, maybe we want to switch to multi-beam so we can see the full extents up and downstream into the channel towards the channel bank of our affected scour zone. Top right, we had some riprap over a footing in the Missouri River. Once again, you can't see into the page. Now you can take the 2D sonar, reorient it, start cutting some profiles. It takes more time, but you can at least get the quick data to see that the profile of that rock layer. But it would take lots and lots of profiles to kind of add it up to see what the overall volume and condition of all the riprap is. So understanding the advantages, disadvantages of 2D and limitations, we'll move on to our multi-beam or 3D sonar. Setup and calibration time can be a challenge. Sometimes it might take a couple hours to get the system rigged out, especially if you're doing it on a vessel of opportunity and you don't have a permanent mount on that vessel. Calibration time, you got to wait for your inertial reference unit temperature to equalize after it's powered up. You also have to drive in your figure eights to lock in your satellites and make sure your boat's heading information is calibrated in with your GPS. It can take an hour, 2 or 3 hours, depending on the conditions, how many satellites you're pinging off of, and a few other conditions. Great advantages of the 3D sonars, it's a geo-reference point cloud, so every single that's tens of thousands or millions of dots, depending on the size of your site, to make up that image, and every single one of those dots has an XYZ coordinate that you can go pick off and find where it is in space. Rough water is not a problem for our multi-beam for the most part. Like I said, we have the inertial reference unit constantly doing that math to correct for the boat moving so that those points get plotted in the correct location. We can start to see underneath footings and then also cover areas at a large time. One other problem we have is dolphins, but I'm not actually talking about pier protection. Talking about these little guys. It's very interesting. There's a site that actually our case studies on in a few minutes here, that 2 of the 3 times we've been out there with multi-beam, dolphins will come and just start swimming about 2 or 3 feet off our sonar head and just playing in the sound waves, which is cute at first, and you get to take some pictures, send them to the kids, but then they block all our sound waves from getting to the bridge. So we're like, hey guys. So we end up just turning off the sonar head for a little bit, hang out, and 10 or 15 minutes they get bored and go find something else to do, and we're able to get back to collecting data. With the georeference point cloud, the GIF on the left, and if we want to talk about if it's GIF or GIF, we can do that at the booth later over lunch or beer tonight. That's what we're seeing in real time. That's about 70-foot deep water in the Mississippi River. We're seeing a step out up high. We're seeing the caisson at the channel bottom, real time from the boat, and then some of that stuff you can see in the foreground. We can clean those extra returns out in the post-processing. On the right, we're starting to see underneath footings. We can measure individual pile heights. We can see that some dolphins have fallen over. In that particular case, we were actually looking for dolphins that had been washed away in a flood and happened across the fact that the footing was undermined with all the piles exposed as well. Can start getting volumes once we switch to multi-beam. Here's another bridge on the Mississippi River. A few years back, there was a barge breakup. They sunk. And then they're actually exacerbating a scour hole, which you can see from left to right, left being the upstream nose of the pier. We can measure the heights of scour, the caisson exposure, and see how it tapers back up. Also seeing some construction debris that was left over at that site, but then we can measure vertical and horizontal dimensions to see the extensive scour. Besides scour itself, we can also monitor scour countermeasures much more accurately over time. Here, we had riprap placed around the pier. Obviously, a little more got dumped in the middle than at the up and downstream noses, so we can see some depressions, the high points, and then also extending away from the pier, how that riprap's tapering. And then it's going to be repeatable over time, so we could scan it in 5 years or 10 years from now and see if we have the same slopes, see if we have aggradation, see if we have rock movement and things of that nature. We can also look at it from many angles. Remember with the 2D sonar, we were kind of stuck in one plane for the most part. Here's a pier that we found was undermined. Very challenging diving condition at this site with some high currents and then various piles and other debris. But then we can go in our point cloud and look at it from different angles to see the extent of that scour hole and how many piles are exposed, as you can see on the bottom right there. And then finally, with our multi-beam, you can get to large areas rather quickly. On the bottom right is a 2D scan where we did lots of tripod drops. So I think we got about 7 different deployments there. So you'd have to drop your tripod, wait for it to spin around probably 2 minutes or so, bring it back to the boat, mark where that location was, then manually overlay all those images back at the office. And you can see high points and low points, but you don't have dimensions on what those elevation of the high point and elevation of low points are, just the general contour based off of shadows and whatnot. But the top left image is I think 11 piers, and probably once we're up and running, that's one pass, about 5 to 7 minutes of sonar data collection, if that long, to get that huge swath of area. We can see the riprap piles around each pier, and if there were scour holes, we'd be able to lock in on those quickly and go in and get dimensions. So it can help us access very large areas much quicker once we're set up. So now our case study. Kevin talked briefly about the visibility that we typically have during underwater inspections. Not only Arkansas, but most of the country has this type of visibility. On the left is the picture of the water, and the right is the picture of what the diver sees. Not much. So you can imagine if you're wanting to monitor a scour hole or a scour repair, you can get the pneumofathometer right up against the pier and get very accurate soundings there. But if we want to start getting 10, 20, 30, 40, 50 feet away from the pier to create a grid of points, the diver is going to become disoriented, and the accuracy of where all those points are getting measured are going to get more difficult to track and much more difficult to repeat cycle after cycle, even more so once we start getting high flows. So at this site, previously they had driven some sheet pile cofferdam, and then they put riprap around that. So on the left, it's kind of some options that we can look at with single beam or 2D imagery. On the left is just a single scan, so we're taking one single plane. You can see there's lots of shadows in that, because if I'm scanning from here, I'll get a real good review off of this face, but not so much off the edge of the table over there because it's in a giant shadow. So here we had a great return off the columns. You can see the top of the footings and the general elevation of the top of the sheet piles, and we pick up a little bit of the channel bottom, and that's probably actually several feet away until that shadow's done casting. To overcome that challenge, we can scan in multiple planes and then stack all those images. So the image on the right, we scanned one time right up against the columns, then we backed up 5 or 7 feet to scan at the edge of the footings, backed up another 10 or 15 feet to scan at the edge of the sheet piling, so that we can stack those images and get a view in multiple planes stacked together as we're looking that way to get more data. And now we're starting to see individual rocks from that riprap, but we still don't have any more depth back into the channel to see how those rocks are tapering down. Just another example of that, the same bridge, single image on the left and either 2 or 3 images on the right. So we get a little better perspective on our footing and seal exposure. Very minor seal exposure there on the right that you can't really pick up on the left scanning from a single plane. And a little better idea of what the rock layer is doing, or the topography of the rocks are doing there. So now if we bring in multi-beam, these are 3 images of the exact same pier. On the left, we have the single scan. You can see a little pile of rocks on the bottom right of that top, or of the left photo, that's sitting just off the face of that sheet pile. In the top center photo, we scanned in multiple planes, so up against the columns, out past the footings, out past the sheet piling. We got a much better view of that riprap directly adjacent to the sheet piling. But we still don't know what it's doing in space. So with the multi-beam, it's interesting because you can see the one piece of sheet pile sticking up in the top middle, and then it is rather prominent in the multi-beam scan as well. But now on the left side of the multi-beam scan, we can measure the taper of that riprap pile to understand if it met spec or if it's moved over time, and the same in all directions. So we've gone from a single plane of 2D to multiple planes of 2D scanning to a 3D model that we can manipulate and look at from every angle on the same site to monitor those repairs over time. So here we got the multi-plane view of the pilot house, and then the multi-beam view on the right, where we can see a little debris of piling, as well as finally getting the slopes of those rocks. Here, I think the first time they put riprap, there was a concern that they were all piled up in one spot. And then after a second job, we were able to verify with multi-beam, and we've monitored over time any movement there, because they've also built a seawall next to a port not far from this site. So it's really changing the hydraulics through this bridge site. So here's our 3D imaging, the same site over time. So this is the same pier scanned in 2019, 2021, and 2023. If you can see individual stones there in the bottom left, got a little gap in data in the center. In the top right, we got one stone there that's rather prominent in all three, which I find is kind of neat when you pick up the exact same rock 2 years apart on 2 different occasions. But then we're seeing the individual stones on the bottom left, and we're getting a lot more smoothness on the top right. So that's an immediate indicator. The picture looks different, it's changed a little. So then we go in and pull our XYZ data. If our elevation's lowering, we're probably losing some rock, it's shifting around. If it's gaining, then that's probably just we're getting sedimentation building up over our riprap layer. One cool feature of this particular software is they have a module called Baseline Comparison. Didn't get a chance to put a video of it in, but you can actually run 2 data sets simultaneously. So in one view, I could run the 2019 data, in the bottom of the screen the 2023 data, and it only shows basically common points. So you're seeing in real time the point cloud getting created for the old data and new data, and that'll, in certain instances, make it really prominent, like, oh, pile of rocks, no pile of rocks. There's clearly been a change here. That's a spot we're going to want to mark and investigate further. And kind of where are we going from here? At the site, they have a new version of the software that we just got the demo on this 2023 scan. It's actually collecting sonar data and LiDAR data simultaneously to create some rather impressive 3D models of the entire bridge site. Might not be appropriate for every structure, but just want to be aware the technology's out there, especially might be something to use before, after construction, verifying that our Scour countermeasures have been installed to spec, and then monitor them over time to make sure they're effective. With that, kind of touched on sonar basics. Speed of sound's very consistent through water, so we take advantage of that to plot distances. 2D's typically in a single plane. You can do it in multiple planes, but you're not really able to get any penetration underneath. And then with our multi-beam, it takes longer to set up as a much more robust system, but it's a georeference point cloud, so we can repeat it and get an XYZ coordinate of every dot in there. With that, appreciate the time this morning, and love to answer any questions, anything we can't get to here. We got a booth, and I'd be happy to talk to you at any other point throughout the day.
With the advancement of carbon fiber dealing in pilings in that type of area, is that given a problem with sonar?
The carbon fiber, I'm not aware with that is a problem. HDPE is, because it'll absorb all the sound. So you have to have the sound wave bounce back to get a return. So I'm not certain on how the carbon fiber, I don't think scan any of that, but HDPE pipe and things of that nature, some of the composites, will create a challenge of imaging the structure itself, just because it won't return the sound wave to you. Appreciate it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.